Am I too loud? Good. Well, they say to save the best for last, right? And here we are. My name is Tzuyang Yu. I'm a professor in the civil engineering department at UMass Lowell. I will be moderating the session on intelligence, machine learning, and transportation innovations. And joining me this afternoon are two speakers. One of them is Dr. Amy Mueller, who is over there. And she's a professor from Northeastern University. And the last but not least speaker is Mr. Charles Major from MassDOT. So I will be giving the first presentation, application of deep learning on the condition assessment of reinforced concrete highway bridges using ground penetrating radar. So please hit it. Okay, before I start my talk, I'd like to ask a question. How many of you like the rise of AI, artificial intelligence? Okay, I see a few hands. And how many of you don't like the rise of AI? Oh, that's still few. And I suppose the rest will be undecided, right? Okay, you know what? Like it or not, AI is rising. So this conference talks about the durability of different things. We develop durable materials for the new generation infrastructure, but we also study the durability of existing structures, how to make existing structures durable. So this talk is about using innovating sensors to make existing structure more durable. Okay. Now I'm going to start with the background information. How many of you heard about deep learning? Okay, but not just for conversation purposes. Well, of course, we have experts also in this area. So I will prepare some slides about deep learning, and then I'm going to show you how we can apply deep learning for the problems that we want to solve in transportation infrastructure. Then I'm going to, if I may, share with you some takeaway points in the conclusion part. Now, concrete, I know that composite is a big deal in this conference, but we also have to worry about the existing concrete structures. In most of the existing concrete structures, they are made of reinforced concrete or pre-stressed concrete. Now you see that they are everywhere. Now, one of the major premature failures cause is the corrosion of concrete structures. And the problem with corrosion is that it takes a long time to develop it. Why is the time an important factor? Is because when we design infrastructure systems, we plan to use them for a long time. And this slide shows you that how long we can actually use concrete. And I know that for the researchers like Roberto, he will have definitely the entire hope on making composite structure to last as long as like concrete structures. And I have complete faith in that. So we have lots of old concrete structures. One of them even close to New England is actually in Connecticut. Now, when there's a corrosion in concrete structures, it takes different stages to develop, and that development takes time. But the problem is at the initial stage, we don't see much sign on the surface. When you see the sign on the surface, it's already too late. So this is a dilemma. When you see the concrete spalling, there's usually no repair. You just have to rebuild it. So this process, as I put on the slides, is caused by the penetration of chloride, and then start with these chemical interactions between the agents and also the steel rebar, by making the rebar as an anode, and then the rebar cross-section will be lost. So the idea for us to use the sensing technology is to be able to capture this reduction of the condition curve. Over time, we know that the condition of your structure will drop, but what we don't know is how fast do they drop. And this reduction of the condition varies from time to time, from structure to structure, because you have different kind of structures, and there are also different kind of loading conditions. So our goal is to make sure that we can capture the trend and such that before the structure reaches the terminal level, we can do something about it. And just to be clear that the failure of infrastructure, in this case, concrete structures, is not really age dependent. Like what I'm showing here, some of the structures actually fails at the age of 40, 42 years, but some of them actually collapse at the age of 26. So there's no clear dependence between the age of the infrastructure versus the likelihood of failure. Now, what is ground penetrating radar? I think many people in this conference have seen this before from previous meetings, or maybe from other conferences. Ground penetrating radar is a very mature technology that has been used in the routine inspection of concrete structures. And there are different kind of scale modes. If you place a guard ring GPR on one place, you get this kind of curve. And then if you move it, you assemble all different curves to form an image. If you assemble actually the different images, you get a volume. So that's what we call the A-scan curves, B-scan images, and C-scan volumes. And GPR has been used in civil engineering for a long time. This is what we see in the typical GPR image. It's usually very noisy, and this is actually from a real structure. And because we don't know the composition of the underground structures, we have lots of different scattering signals from here. And so let me go back here. The challenges we want to present it to AI to solve the problem, because if we can solve the problem by using conventional approach, we don't need AI. So the problem we want to bring to the AI must be something that we human beings cannot really solve easily. So they are the reasons I listed here, because there are lots of many unknowns, multiple scattering, or the problems that we know. If we know this condition, we don't have to do the inspection. So that's why we have to use GPR. But because of this unknown, it is almost impossible to decipher this using conventional electromagnetic scattering theory, because we just cannot do that. There are too many unknowns. And real image GPR images can be as noisy like this. So I took the liberty to prepare some slides for the audience who do not consider AI as their bread and butter. I think that everybody heard about AI, but not everyone's doing AI for research. So what is AI? Well, this is actually, I modified some images up here. So AI is basically a study, a word was coined by John McCarthy from Dartmouth College back in 1956 in a conference, like here, like this. He proposed the idea and people start studying. And within this domain of AI, there are different kind of areas. One of the areas is called machine learning. Machine learning is basically an area trying to teach robots to perform the task. So the task is usually very clearly specified. In the past, this area is also referred to as the software computing or system identification. And actually, I learned this back in 2001 at MIT. So this technology has been there for a long, long time. So why did this AI actually all of a sudden become such a hot topic nowadays? It's because in one of the areas, which is at artificial neural networks, this area offers unlimited flexibilities for all kinds of problems, starting from images, signals, or even videos. So this deep learning is actually part of this machine learning is under this artificial neural networks. The difference is traditional artificial networks usually have a very shallow layers. So they only have one or two intermediate hidden layers. A deep learning is usually the one that you have many, many different layers. So the question is, how deep is deep? How do we know that it's too deep? That's a question that we are still trying to figure out. So this is just about the definition. Now, the vision that people see deep learning for civil engineering applications is how do we actually can use them to bring us the knowledge out of this perfectly matched and fitted result. That is something that I think that for researchers and the audience to really think about it, because I am a skeptical researcher when I take on this AI journey. And I always ask a question that who is learning here? Is the machine learning here or we are learning here? Is it more important for us to learn or is it more important for the machine to learn? And once the machine has learned, then why are we still here? So we did some literature review and we found that this machine learning has been used actually in civil engineering since around the 2000. There are lots of different applications since, and if you look into the literature, this is probably the most rapidly growing area in inspection and monitoring, which is by the use of deep learning and machine learning. Now, if we focus our literature review on the use of GPR, still there are lots of papers published in this area. We have seen that for all different kind of problems. And this is the global phenomenon that people are using deep learning to solve difficult, challenging engineering problems. So what did we learn? And there are, of course, many detailed parameters which I can share with you if you're interested. But overall, we found that the design of the architecture is something very tricky. But after trying a number of different patterns, we realized that this architecture has a rule, which is the size of the filter and the number of filters should follow this inversely power law. So when you have a very large size of the filter, you should reduce the number of the filter. And when you reduce the size of the filter, you should increase the number of filters. So this is the inversely related relationship, which we found that very useful, which gave us a very good result. And I was having a conversation with some colleagues in the conference. They asked me that, what if I change different functions? What if I change the activation function? How the results going to be different? And I will show you that in the end, it does not matter. Why it doesn't matter? It's because the data we want to give it to the AI to solve has another factor, it's called time. So we propose this called power to net. That's the model we want to use. Now, what's the data? So this is the process of corrosion process. But in order to validate the model, we have to use some existing known specimens. Otherwise, the fundamental assumption for non-destructive testing is that it is non-destructive, meaning that we will never be able to get the ground truth. Because if you open up the structure, that is not non-destructive anymore. So you cannot get the ground truth. So we cast the samples, which we know exactly the corrosion level. And then we inspect the specimen multiple times in different angles, at different frequencies, and we get the correlation between GPR images and the surface condition and the actual corrosion level. So these non-samples are very important in training our neural network or the deep learning model. After that, so this is actually the images we trained them. I only present some of the levels. So after training it, by the definition, we call the samples S1, S2, S3. S1 is supposed to be the one without damage, and S2 is the one with damage. And then you can see the prediction of this actually is very close to what we assume it to be. So S1 is supposed to be level 1, S2 is supposed to be level 2, but in one of scan, the model predict to be Tzuyang. That means that you cannot take just one scan, you have to take multiple scans. Now this is the architecture, but I'm just going to move to the data. So what's the challenging problem that we have here? We choose a bridge, which is I-95, and we pick 7 columns. And on these 7 columns, we continue monitor the same 7 columns for over 2 years on 186 days. And each column, just make sure that we don't get just one scan, we scan 3 at 3 different locations. So in the end, we have more than 3,800 images over the 2 period of time. And this is actually what we believe the results should be. And this is actually how the students, and we take the pictures, we correlate the thing. And by extracting the features from one single image, this is actually the 256 features that you can extract from one single image. A lot of information that the human mind just simply cannot process. And this is the model we use. Now, here's the interesting part. The time is actually over 160, 186, 82, because some columns we just couldn't get the data. Now, the result we found is that from the predictions, some columns without much change on the surface, the corrosion level actually increased. And then, of course, there are some fluctuations. Why? Because there's weather. The environmental effect actually will fluctuate the weather. So which tells us that you don't want to make the judgment just based on one point. You want to take the average and over a long period of time to make the decision. And sometimes even the model will be confused. So there's some fluctuation on here, but if the cracks is not significant, this fluctuation is not going to be that severe. And this is another one which you show that the fluctuation of this, which means that the model is still deciding that whether the corrosion has been increased to another level or not. But over time, the model has converged. And in some cases, the model has no confusion, but this is the column actually close to the middle of the bridge. So it does not have much environmental effects, but it also shows the increased level of corrosion. And this is another one, which shows some fluctuation to represent the environmental effects, but overall, it does not predict the increase of the corrosion level. Without this deep learning model, we could not do this kind of prediction because the only thing we have is the surface image, the visual, and the GPR image. So now for the no correct intact columns, the model says that there's nothing changed. So in conclusion, I hope that you are somewhat convinced that this deep learning approach is really, really robust and can be used to address challenging and practical problems like this one. And after we finished collecting the 3,800 images, my graduate student bring it to me and asking me that, Professor, what do we do with the data set? And I told him that maybe we can sell it because the real data are so expensive nowadays. It took us 2 years just to finish data collection. But what is even more important here is what do we learn from training these data sets? That is, I think that's something for maybe other speakers today could actually share with more other valuable suggestions and insights. Okay, so with that, I'm going to move on to the next presentation. Okay, well, thank you for your time.